welcome everybody for the exciting week that we're going to have with 5 different talks by people coming from all over the world, basically. Well, they just came from João Pessoa, actually, which is very nice. They came before from all over, and it's my great pleasure to introduce my ex-colleague when I was living in Belgium, Horsten, who is now in Great Britain, in Bristol, which I was told is the most exciting place to be, and there are open positions for postdocs in Bristol.
No, permanent lectureships.
What's that?
Permanent lectureships.
Permanent. Okay, even better. So this will be advertised at good time. And thanks everybody for coming. We will start the week with this talk on infinitesimal probabilities. I just wanted to advertise the next talks, which will happen on Wednesday and Friday. On Wednesday will be some deductive logic by Vladimir and assertability by Hit. And on Friday we will have a lot of model logic by David and Giorgio, talking about proof theory and model theory, perhaps formal semantics of model logic. And we're all invited to come. We have a mixed audience. We have some students from computer science, we have students from philosophy, not much else, but I apologize in advance if people come late. Sometimes they arrive a little bit late. And let me then announce again Leon, and welcome him to give the first talk to me on infinitesimal probabilities. Thank you very much.
Thank you, Joao, for inviting me to give a talk here. It's great that we meet again after not having seen each other for 8 years or so. Going back 8 years, we were indeed had a position in the same place. Okay, so what I would like to talk about is infinitesimal probabilities. And I think some of you have, in preparation for this talk, looked at the paper by somebody on Landmarkers, I believe, on infinite loteries in the natural numbers. So, the structure of the paper is going to be the following. I'm going to just start by motivating what I'm going to talk about. Then I'm going to sketch how the theory of infinitesimal probabilities looks like, or should look like, in my view. I'm going to talk about some of the properties of such theories, and towards the end I'm going to hint at some further developments, or questions that people might want to ask themselves. And concerning this last question, actually this is something that where I could use some help with, is namely suggestions for things that I should be thinking about. That would be good. And this talk is going to be kind of an overview talk, so I'm not going to be very technical. I'm going to try to explain the motivation behind what I've been doing, and also some of my collaborators have been doing. It's not going to be very technical, so in particular, I won't. This talk won't contain any proofs. Okay, concerning the motivation is what's behind this is roughly the following. So, a theory of infinitesimal probabilities will be inspired by non-standard analysis, and non-standard analysis has been developed, I think, in the 1950s already, and it's a well-developed branch of, or what should I say, logic or analysis. I don't really know what to say. And the reason is that even though it's well-developed, so it was developed by Abraham Robinson and his followers, it has never really caught on in analysis. So this is the theory that goes back to Leibniz, in which analysis is developed as the theory of the real line, where the real line is supposed to contain not just the real numbers as we standardly understand them, but also infinitely small numbers. This was an idea of Leibniz, but it was not until the work of Robinson that it was established that this can be coherently, rigorously developed from a mathematical point of view. But it's not really caught on, and the reason is that, although of course it has had a following throughout the decades, there are people working on it right now, but it's never become very mainstream. And the reason is that that analysts have the feeling that it doesn't really give us anything new. And the reason is the transfer phenomena are behind this. If you can prove something in standard analysis about the real numbers, if you can prove something about the standard real numbers in non-standard analysis, then there will also be a proof in standard real analysis of it. This is a theorem that can be shown. So since we're all used to working in the standard framework for real analysis, there doesn't seem to be much motivation for analysts to start working in non-standard analysis. Even though it can be more, certain arguments can be more intuitive and so on and so forth. So there is a danger for non-Archimedean probability theories that there's the same worry, right? That you can say, okay, so what's going to be new here? If nothing's going to be new, if you're just going to give us new theorems, old theorems, new proofs for old theorems, then you're probably not going to be very much interested in probability theories. Okay, so that's a motivational problem from a mathematical point of view. Then there's also a philosophical stumbling block, namely one can say, well, perhaps there is a coherent mathematical theory here, but maybe from a philosophical point of view, this whole enterprise doesn't make much sense. And this would be the kind of objection that Cantor was confronted with at the end of the 19th century, where people said he was developing the transfinite set theory, as we would now call it, the theory of computing with actual infinities. And many people who were prepared to concede that this is mathematically coherent, even though there were doubts, some people had doubts about that too, would say, look, from a philosophical point of view, this doesn't really make much sense, because since the days of Aristotle, and certainly since the Middle Ages, we know that the idea of actual infinity is, as realized in the world, be this the physical or the mathematical world, is incoherent from a philosophical point of view. That's what philosophy is taught us. So Cantor had to not just develop his mathematical theory, but also had to fight this philosophical battle. So he had to diffuse all the arguments by Galilei and other people against the possibility of actual philosophical arguments, against the possibility of the philosophical coherence of the idea of actual infinity as realized in the mathematical world. He fought both battles, and in the end he prevailed. Well, not him, but afterwards people came to recognize, yes, he's right. Now, here, when we talk about non-Archimedean probability, we will also have a philosophical battle to fight. There are, especially the past 10 years, philosophical arguments have been developed and multiplied against the philosophical coherence of the idea of non-Archimedean probability. I'm going to put that aside here. I'm happy to answer questions about that in the discussion, but here I'm going to be occupied with the mathematical theory of non-Archimedean probability. So what's the motivation? Well, here's what classical probability will tell you. Fair lotteries on finite sets can be modeled in probability theory. We know this certainly since Laplace, that if you have a lottery with n tickets, if it's a fair lottery, the chance of any given ticket winning is 1 over n, the ratio formula. We know that. No problem. It's the paradigm example of an application of probability. Okay, fair lotteries on uncountable sets, such as the reals. Yes, that's possible. There are uniform probability distributions on the real numbers, but every ticket, every real number will have to be given probability 0. That's the only possible answer. Fair lotteries on countable sets. That's a nonsensical question. It doesn't exist. It's complete nonsense. There is no answer. So when you say, he or she will say, this question does not make sense. And I find that really strange. If a fair lottery on a finite set makes sense, on an uncountable set makes sense, then one on a countable set should also make sense. This is just from a conceptual point of view. But I think this is a moment where I pause. Like, what's going on? Why? That's the motivation. So, what do we want? I would like to be able. I think that a fair lottery on countably infinite sets is conceptually coherent, and as mathematicians we should be able to model it. That's what I think. Classical probability theorists would say, no, sorry, this just doesn't make any sense. Okay, so we have to be able to come up with uniform distributions, probability distributions on countably infinite sets. We have to be able to do that. Also on uncountably infinite sets, also on finite sets. We already know how to do that to some extent. Now concerning probability distributions on uncountable sets, as I said, if this is going to be uniform, it's going to be uniformly zero. I don't like that answer. It's an answer. That's good. It's an answer. It's a possible answer. Yeah, I don't like this answer because it collapses remote possibility into impossibility. It doesn't make any distinction between impossibility and infinitely small possibility. I would be a priori inclined to say, yes, it's possible that my real number is the winning ticket. It's just infinitely small, but not zero. But that's not something that classical probability theory can countenance as a reasonable answer. I think that the distinction between impossibility and possibility should be reflected in the probability functions, if possible. That request is known in the philosophical literature as regularity, also in the mathematical. Only the empty set is given probability zero. So if I have a ticket, it's a singleton. It's going to be larger than zero. So remote consistency has to be distinguished by the probability function from impossibility. Then they're maximally finite rates. Also, there's this problem of the non-measurable sets. Of course, we are here philosophers and pure mathematicians. We like non-measurable sets and the axiom of choice and all of that stuff. But if you go to the probability section of the maths department, they try to ignore the non-measurable sets. They know that they exist, but they don't like them. They think they're monsters pathologies. So they know that if you have a big sample space, there will be lots of events, subsets of the sample space, that have no probability associated with them at all, and cannot have. That's what maths tells us. That's what the axiom of choice. That's the message of the axiom of choice. But again, from a conceptual point of view, you think, how is this possible that a certain event does not have a probability of occurring? Not a probability that it's 0 or 1 or anywhere in between. There's no probability value attached to it. So for instance, if I want to do utility theory, and I need to base my utilities on those kinds of events, what am I going to do? What formula am I going to use in order to compute my utilities and to come up with a reasonable answer with respect to what I should do? So I would like to give all properties of sets, so all subsets of the sample space, a probability. So I would like all sets to be measurable. Okay, so Kolmogorov probability, we know it, so I'm going to be fast here. We have a sample space, we have a sigma algebra on the power set of the sample space. The sample space is called omega, and those are the measurable sets according to the probability function that we're going to base on it. And this probability function is going to be defined on the algebra. Outside the algebra it's not defined. And what do we want? When does a function count? A function on this algebra count as a probability function? Well, it has to satisfy the axioms of being a finite probability measure. And I'm not going to go through these axioms, I'm assuming that everyone's familiar with them. And this is a crucial thing, sigma additivity, countable additivity. If you have a family of, an infinite family of pairwise exclusive events, so the intersection between any two elements, the empty set, then the probability of the union can be computed on the basis of the probability of the constituent parts, using the familiar formula. And this is crucial for the probability theorists. Because that means, so here you see the limit concept occurring, that means that analytical methods can be brought to bear to probability theory. And for instance, you can model loteries on countably infinite sets using finitely additive probability functions that do not have sigma additivity, and philosophers do that all the time. If you look at the philosophical literature on this, you'll see this popping up here and there. But mathematicians are thoroughly unsatisfied because they say, well, that's not really probability theory anymore, because probability theory is analysis. That means we have to be able to take limits somehow in a reasonable way. And if you throw this out, then you're taking it outside our sphere, so to speak, and it's non-probability theory. Okay. Right. So this sigma additivity rule is taken to be pretty crucial in probability theory. Not among the philosophers, but among the probability theorists. So as I said, there are no fair loteries on countable sets, and sigma additivity is of course the reason why there isn't. There are fair loteries on uncountable spaces, but probability functions must take value 0 almost everywhere. So a massive failure of regularity, desideratum. Oh, and by the way, interrupt me whenever something I say is not clear. And there are lots of non-measurable sets. We assume the axiom of choice, which we do all the time. So from the classical point of view, the project of modeling these infinite loteries set in a way that satisfies some of the desiderata is a hopeless task. Everything. Now, I'm going to sketch how non-Archimedean probability theory should be developed in my view. But probability theorists are probably, well, when I talk to probability theorists about this, they say, well, look, probability functions are just almost by definition now probable or classical probability functions. So if you're going to do something else, don't call them probability functions. And that seems to me kind of a terminological dispute when it's arrived at this stage. But I'm happy to accept that the probability theorists have patented the term probability theory and the use of the term. So what I'm interested in, is give a quantitative theory of possibility that's applicable to the situations around. And if you say, well, call it a quantitative theory of possibility, but don't call it a probability theory, I'm happy with that. I don't mind. I really don't. But I want them to be at least finitely additive, and they will turn out to take values in a non-Archimedean extension of the number. So we will make use of these infinitesimals as Leibniz, Robinson. But I do want an infinite additivity law. Actually, I want perfect additivity. So if you have an uncountable space, I want to also be able to express the union of an uncountable family of events. The probability of the union of the probability of an uncountable union of events in terms of the probabilities of the constituent events. It's called perfect. So I do want an infinite additivity law that has to be connected, and it will have to be connected to a limit concept so that analytical methods can be brought to bear on probabilistic models. satisfy uniformity, regularity, and totality, as I said in the earlier slide. Now, this is what I'm developing mathematically is related to work by analysts, logicians from Pisa, from the University of Pisa, namely Grande, Mauro Di Nasso, and Forti. Marco. And what they try to do is the following. And so I think their work is important. But I think, well, I'm a philosopher, and I think they're not giving their work the right spin. The way they present it, it will never catch on. So I'm trying to give this another turn, so to speak. But mathematically, what I will be doing is somewhat close to it. What they say is that, look, when it comes to transfinite sets, there are these two principles that are in tension with each other. There's Hume's principle that says that if two sets are in one onto corresponds with each other, they have the same size. Hume's principle. Okay, Cantor maintained that, right? Standard set theory satisfies it. Classical set theory obeys it. But there's also this old principle, which is called the Euclidean principle, that the that the size of a whole is larger than the size of its proper parts. Right? You go back in the mathematical, philosophical literature, you'll see this principle popping up. Cantor drops it. But they say, look, we can also drop Hume's principle and accept this Euclidean principle, and then develop transfinite set theory along those lines. That's what they do. So they call this the theory of numerosities. They develop it, and well, I should have read more about it, but that's what they do. I think it will never catch on because no one's going to. Well, some people will. Very few people are going to side against Cantorian transfinite set theory nowadays. It's just not going to. And there are lots of reasons for it. Non-well-founded reasons for it. So behind it. So I think this is but the mathematics that they use or that they develop is close to what I want. And it's all related to ultrafilters. And many of you here will know what an ultrafilter is, but I will try to explain it. So suppose you have a set. So an ultrafilter, suppose you have a set. It has lots of subsets, right? We know that. And we want to classify these subsets into two different sorts: the large ones and the small ones. That's what an ultrafilter does. An ultrafilter will classify some of these subsets of a given set as large, and the other ones as small. How does this work in more detail? Well, the following. So a subset is an ultrafilter is a bunch of subsets of the set you start from, the large ones. Which ones are large? Well, the empty set certainly isn't large. The whole set better be large, otherwise there's no large set. And then largeness better be closed under the superset property. Right? If you have a large set, and you have something which is a superset of it, then that better be also classified as large. And then there's this finite intersection property, which says that if you have two large sets, then their intersections ought to count as large. But what you don't necessarily have is an infinite intersection property. So you can assign finite intersection. And the ultra part means that every subset of S is classified. No sets are considered, well, neither large nor small, right? This is black and white thinking. So that's what an ultrafilter is. So if you have 1, 2, 3, then you have the notion of a filter. If you have 4, then you have an ultrafilter. And we will be interested in what are called fine ultrafilters. And this is a concept that's well known in set theory. And it means that if you have an element in your set S, right, so it's all about the set S and its subsets, if you if you look at all the subsets of S, if you look at all the subsets of okay, right, I should have said something about the set I'm now going to start. So now I'm going to start with a set of finite sets. I have to explain this notation. Set here, notation. Some of you may know. This is the collection of finite subsets of a given base set S, right? And what we want is an ultrafilter on this set, on a set of finite sets. That has a certain property called finiteness. And what does that mean? Well, it means that the collection of all finite subset of all finite subsets of S, which contain a given point, say A. So you take an element and you look at all the finite subsets of S that contain an element. That's a bunch of finite sets, right? So that's a candidate for being classified as being either small or large. And finite says it's large. That's what it is. Okay, is that the concept more or less clear? Good. So that's right. So what are we going to do now? Well, this is a sketch of how it works, but here's what we do. So we have our picture. We have our set S, and we have an event A, which is a subset of it. And our question is, what is the probability of A? This has to be defined. This has to be defined. Okay, what do? We look at all finite subsets, okay? So, S1, S2, S3, S4, and so on. But there are infinitely many of those. If this S is countable, then finite subsets, right? These are the finite snapshots on which we're going to test A. So each S n will be a question. There will be a question. What's the probability of S on this finite snapshot? What's the probability of S on that finite snapshot? So for here it's 1 finite snapshot. The conditional probability of A given S4 is 1. The conditional probability of A given S1 is 0. The conditional probability of A given S3 is 1 over 4. But I collect them. Right? So that's what I'm doing. So we have this. We start with a fine ultrafilter on the class of snapshots. And it will be this ultrafilter which determines our probability function. We can also add a weight function to it. I'm not going to go, this would complicate matters a little bit. So we start with this ultrafilter, that's given. To have such an ultrafilter, you need the axiom of choice. So this is not a constructible object, but certainly it exists according to standard set theory, and that's what I'm going to assume throughout. So I'm going to part company very these people by just assuming standard set theory. So I assume throughout. Okay, we start with an ultrafilter like that. It must be solved. And then we look at the collection of all these snapshots, right? So if we have a finite snapshot, one of those guys, then we can, using the ratio formula, Laplace is given to us, compute the probability of A given S. So this is just Laplacian probability. We're going to use it. That's not going to be our ultimate probability function. We'll use it. Collect all these snapshots. And that's going to be our sort of proto-probability value. We're going to say, let's call that a number. Well, you can't call that a number because you can't add them, you can't multiply them, and so on and so forth. You have to do something with them before they deserve to be called numbers. What do we do with them? Well, we identify them modulo ultrafilter agreement. So that means that if you have two events, such that on a large class of snapshots they agree as to what their probability value is, condition probability value, then we're going to say they're equal. So for instance, take that, suppose that our sample space is natural numbers, then we could say, well, let's take the set of n without 0. You can also take n without the number 1. There will be snapshots on which these two, so A is this, there will definitely be snapshots on which give different probability, conditional probability to these two guys, right? But there will be few of those. The collection of snapshots that agree will be large, given that we have a fine ultrafilter right? And similarly, we could say, well, let A be the number 17, and B be the number 21. There will be snapshots which will give them different conditional probability values. But ultimately, if I buy the ticket 17 or the ticket 21, if this is going to be a fair lottery, they better be identified these two numbers. And that's what our ultrafilter agreement does. Okay, so we have this. So we take the probability value of A before normalization to be the equivalence class of all these collection of snapshots that agree with the snapshot associated with A according to the ultrafilter. That's what we do, right? And then that's really the only trick. Yes.
Just a question. The condition that defines the equivalent relation is the probability of I given F, or just the probability of.
Sorry.
It's the probability of A
yes,
given
yes,
F and B
given
given
F.
F.
Sorry, this is
Okay.
yes, statement. Probability of A given F is the same as probability of B given F. So it's always conditional type.
It's always conditional.
Conditional probability. Yes. Yes. That was a mistake. Right. So the range of P. So now we reel in the basic apparatus from non-standard analysis, and we say the range of this probability function forms a field by the ultrafilter construction. It will be an all-Archimedean field. This is all. Well, this is just non-standard analysis that tells us that the reals are canonically embedded in the range of the probability function. Addition and multiplication can be pointwise defined. And since this is a field, we can divide, right? Divide, multiply, and so on. So if we have one of these pre-normalized probability values, we divide them by the probability of omega your sample space, whatever it is. Then the maximum probability that will then arises is one, and the whole thing is normalized. But that's the thing. So probabilities behave like and can be seen as limits of countable snapshots. So there's a concept of limit here. So the probability of A can be seen as the conditional probability, namely the probability of A given a finite set on which it tests, as this intuitively, as this finite set becomes larger and larger and goes to infinity. This is just, yes. And we could add a real value equation, but that's all. And then we can also define the notion, we can define infinite sums. Again, in the same way. So we use this limit concept. So we say, so if you have an index set, and this index set could be your whole sample space, large number sample space. And suppose that for each index set, there's a real associated with it. Then you can ask yourself, what is the sum of all those unions? Well, we define it as a limit, as is done in classical analysis, namely a limit of finite sums, right? So your index set intersected with a finite set. This will be a finite set of real numbers. It will have a certain, this will be a finite sum of real numbers will be a real number, but this limit takes it to infinity. It's the limit of all those. So you test this sum really on finite snapshots again. So it's the same phenomenon. So we have this concept of infinite sum, and as I said before, what we want is a reasonable infinite sum rule. We want to compute the probabilities of infinite unions on the basis of the probability of the components of this union. So if we have a family of pairwise disjoint sets, and this family can be as large as your sample space, then the probability can be of cardinality of the sample space, then the probability of this union can be seen as the limit of the sum of the constituents in this way. So using this definition, this comes out. And this seems to be the right analogy for the infinite sum rule that we have in classical probability theory, but it's perfect additivity in the sense that we're not requiring this family of sets, this index set, to be countable and countable to sample space. Okay. So what are the properties of this probability function? Well, the range of the non-Archimedean field, as I said, one standard analysis roughly. P is a finitely additive probability function. We have, of course, these things have to be all have to be verified with, but this is stuff. We have what I think to be a natural infinite additivity law, and the probability function will be uniform, regular, and total. So this works. So I started with an event. So this was the event, and in the end I assigned a probability to it. But this was arbitrary. So no conditions on it. So that means all subsets of the sample space that you start out. Also, this is a real numbers. We'll get one of these non-standard probability values using this procedure. So it's total, it's regular, that's where we need the notion of fineness, and it will also be uniform. And actually, this also, to prove that the probability function that we end up with is uniform, we also need fineness conditions. And that already tells us something, namely that we do not start with any ultrafilter on the finite snapshots, but we impose a condition, fineness, to get some properties out, namely regularity. I said I want regular probability functions. I don't like this answer that the analysts tell me that it always has to be zero, even if I have a ticket. Probability theory tells me that probability can be zero. I don't like that because the ticket is better than nothing, and so on and so forth. But if I want that to come out, I have to impose a condition on the ultrafilter. Otherwise, I don't get it. And as I said, you can add a weight function to it too, but we're not going to do it. So what is a probability function? We need a sample space. We don't need to choose a sigma algebra because it's going to be total, but we need an ultrafilter. So classical probability theorists have some choice to make here. Sigma algebra, we have a choice to make. Ultrafilter, well, it's not really a choice because the actual choice is. And then the classical probability function said, and have a weight function. Well, we can also add a weight function. That makes no difference. That's why I'm not. So that's what a probability function really is. Now, what are some properties of these probability functions that I'm talking about here? Well, first of all, we have this Euclidean property here. And I think for probability values it makes sense. I think for cardinalities it doesn't make sense. Now I want to reiterate this as many times as you will give me the occasion to do so. I'm going to accept transfinite symmetry. I'm not going to mess with it. That's the theory of cardinalities. But for probabilities, I think this Euclidean property that the probability of a whole, of a larger set of atomic events must be bigger than the probability of a proper subset of it. I would like these probability functions to be as fine grained as I can get. So we have this. This will be a property. This will be the property of all the probability functions. And okay, will we have some invariance properties? Well, no, we won't. So this is something that we won't have, and I don't mind. There will be something that I do mind, but that's for the next time. So what is it that I don't mind is that if you have a set, say we're talking about the natural numbers, right? We have a set of natural numbers, that's our event. What's the probability of it? Well, if you shift this set by adding a natural number to each of the elements of the set, then you should say, I've just shifted the set. It should be the same probability. No? No, not always. And the reason is that if you, for instance, well, we were talking about the natural numbers here, we were talking about other infinite collections, or infinite sample spaces, pretty much the same way. Suppose we have suppose our event A is the whole sample space, and suppose our shift is just plus 1. Then A plus 1, well, then A plus 1 will be the natural numbers about 0. But this is a proper subset of that. We'll have small probability by the right? And I think this is just not that. But one may ask the question, for instance, well, but what kind of invariance properties can you get? You can get one full, but I'm not going to.
Hubert needs this property for his hotel.
For his hotel.
Shifting.
Yes.
Things
Yes. So, as far as cardinalities go, fine. No problem. I'm not challenging them at all. Permutation invariance we also don't have. So there are some permutations of our infinite sample space under which probabilities will not be invariant. I'm not going to give this argument. I can give an argument fairly quickly in the discussion of the Okay, so the message here is translation invariance, permutation invariance, rotation invariance, and so on. No, you're not going to get that. Right? I mean, there are lots of things you can ask, but the rough message is no. Here's a worry. The worry is that, well, we said that your probability function is relative to choice of outcome. So that means that if I have one sample space, and I have all these desiderata, and I have my recipe, one ultrafilter, and I have the event A, one ultrafilter will tell me that the probability is this, say a half, but maybe another probability function will give rise to a probability function, another ultrafilter will give rise to a probability function that says that the probability of that event is 0.7. Could happen, could it not? Yes, so that's a word. That is a word. That is a word. And especially when you think about how many ultrafilters there are. So if you have a sample space of cardinality kappa, then 2 to the 2 to the kappa is the number of ultrafilters that you have to choose from. And how much variation in assignments of probability values is hidden in this mass of ultrafilters? That's the real thing. And it will not go away. I can only try to limit it. It's the best I can do. And already I tried to do that a little bit by saying, well, I'm interested in regular ultrafilters, in fine ultrafilters. many of them. So well, but it's a condition that gave me some properties of the yes.
I have a question. If you change the alter filter, can it be that an event A that had greater probability than event B turns out to have
yes
smaller probability?
yes. There are lots of things that
Not even that is preserved, not even the order.
No. So yes. So we want to limit this, try to limit this by imposing constraints on the...
There is another question.
Oh, yes.
You said that the probability of the set that finds is a subset of the other. You said that A is a subset of B, probability of A is larger than the probability of B. Yes. Okay? So when you say that you're using the same ultra filter to both, or you can use different ultra filters for each other.
Sorry? No, so this will be preserved over probability function. So no matter which ultra filter you choose, you will always have the fact that you will always get the result that the probability of a proper subset is strictly smaller than the probability of a proper superset. Okay, so I was going to say something. Again, remember that?
I was asking about the preservation of order when you change the alter filter.
Yes, it's not always preserved, because then I would be very happy that it is. Oh yes. So in particular, this relates to the measurable sets, the non-measurable sets. So what I said is, well, look, there's this problem of the non-measurable sets, and probability theorists don't like them. So I would like to give them a measure, a probability value, and I did. But then in the end, if for given a non-measurable set, depending on which ultra filter I choose, I can give it any probability I like, and I haven't really improved on this problem of non-measurable sets, I would say. So it's a big word, and that's all to be said.
Sorry, just a second. You said you can give all probability you like, but I mean, is it a theorem?
No, there are things that need.
There are some limitations.
There are limitations, but there are things that need proof.
Okay.
So, no, there are very few results at the moment, but it's not because it's really hard, it's just because nobody has solved.
But as long as the event is contingent, you can shift it as
No.
more probable, less probable.
No. So, for instance, this is a contingent event, and it will get minimal probability always, and always the same by all ultra filters. It's not saying much, but it means that at least the strong statements that you make, it's a bit too strong. So, there are questions. So, here's one thing. So I said that permutations don't preserve probabilities always. Let's say, shifts don't always preserve probability. That was okay. What about? It's always good in this context to think about the natural numbers. That's an inspiring case. Right. So what we would like, despite that. So despite that, I would think that the probability of the evens and the odds should be pretty much the same, up to an infinitesimal at least. I would think. Despite the fact that they can be one-to-one, that there are always mappings and permutations and what have you, and can mess around with it indefinitely. Right. Do we get that? That the probability of the evens and the probability of the odds are the same in the samples when the sample space is dimensional. No, we don't get it for free. If we take our ultra filter on, and the reason is roughly that if we take our ultra filter on all these snapshots, then these snapshots can be so disconnected that that the class of test sets on which they are close to each other, the evens and the odds, is not classified as large. Somehow what you have to do is to make these snapshots, I've drawn them as somehow local, right? But nothing in my definitions makes them local. So it could be one object here, one object there, and one object there. So you have to build in some sort of connectedness or locality. Okay, so how can we do that? Well, we've taken our ultrafilter on the class of all finite subsets. Now I say, no, I want to take my ultrafilter, my finite ultrafilter, on the connected, on the really local snapshots. They should not just be small, but also local. What does that mean? Well, it could mean, for instance, it means several things. But it could mean, for instance, that concerning the natural numbers, you only take intervals, MN, right? And you can already see that when you take any interval, there will be about as many evens as odds in any interval. And then if you make these intervals larger, well, then it will become closer and closer and closer to half evens, half odds, right? So that's one way to do it. There are other ways of doing it, right? Okay. So for the natural numbers, but that works for the natural numbers, and something like this would work for the rationals and the real. But how about if you do this, for instance, over set theory? Right? So what's a connected snapshot in a part of the set-theoretic universe? Strongly inaccessible part, for instance. We have to do some work. I'm not going to go into that here, but it means that it's not completely trivial, but some things can be done. Right? So, as I said, now I can give a more informed answer to Joao's question. He asked, well, can the orders reverse? For instance, the even and the odds, yes. I mean, if you know constraints, so all snapshots are okay, then I can make the evens 0.1 and the odds 0.9 by tinkering with my ultrafilter. But if I impose this constraint, that the base of this ultrafilter has to be intervals, or initial segments of the maximum, or something else, connected snapshots, can't mess with it. So this is one thing that you might like to do. Another thing, and I'm just going to mention this in passing, is, well, we've talked about this is a countably infinite domain, but what about the real numbers? Wouldn't you like, for instance, to have the uncountable subsets of the real line to have smaller probability than the uncountable subsets of the real line? That seems a reasonable request. Even if you give up use, for example, it still seems reasonable. Will you get it? Not for free. But if you impose the conditions on the ultrafilter, then you will get it. So that means we have to try it. So the message is impose all the conditions on the ultrafilter. I'm not going to go into details, but now I get to the last little part of this, and going to be a few minutes, namely, what kind of questions should I be asking? Yes, you have a question.
Just a short question, because you mentioned conditional probability.
Yes.
I was thinking about the Bayesian theorem. In an infinite lottery, for example, do you still have a Bayesian theorem? Because one might ask something like, what's the probability of the winning ticket be an even number, given that such and such?
Yes, you do. So, for instance, what you might ask is, given that I draw either ticket number 1, 2, or 3, what's the probability that I will draw number 2? So, from a classical point of view, this cannot be computed because you divide by 0, and Bayes' theorem will not be of any help to you. But here, it will just be 1 over 3. It cannot be replaced. And that's where regularity does some work for you. So in updating on remote evidence, remote contingent events, such as that you draw 1 or 2 or 3, that's where this machine can help. So yes, this could be one of the applications that I talked about. This is on the local dot. So How is this framework related to other ways of generalizing probability? Well, there are lots of conditional probability theories where they take conditional probability as a primitive. And the most famous one is the Doppler functions. And you can ask yourself, how do these non-Archimedean probability functions that I'm talking about relate to these Doppler functions? And here one can prove a representation theory, namely of that.
Can you remind me what a Doppler function is? I don't.
Oh. No, I can't, because the reason is that
I'm a little bit rusty on this.
It's a function that it's a function from so you have a language, call it L, and you have the probability of phi given psi. Those are the things that you get, and this will be a real number, always a real number. And you can conditionalize, and you can conditionalize on contingent events that have probability 0. So that's a good thing. So that's how it improves on standard probability. That's what you can do. But for anything that's not the empty set, so C of dot given psi, if psi is not the impossible event, and this is a classical, is a common function. It's a second good thing. Cool, thank you very much. That's a second good thing about these Doppler functions. And then a few more axioms are written down governing their application. And these were written down by Popper, and they are a bit unintuitive. That's why people think, well, is this really a probability-like thing? And you have finite additivity. Yes.
He was interested in axiomatizing evidence and the impact of evidence on.
Sorry?
He was interested in evidence, in the impact of evidence on conditionalizing.
Yes. He wanted to conditionalize on very improbable evidence and the standard. So this logic of scientific discovery in 1950 or. So he said he just wrote down a bunch of axioms governing, and I think he was just lucky that the whole thing was consistent. I mean, when I look at these things, what's behind this and what's that? Okay, so but one can ask, but we now know that it's consistent and so on and so forth, and these things are used in philosophy of science and philosophy of language. But one can ask, how do they relate to non-Archimedean probability? What one can prove is the representation theorem saying the following, that for any non-standard probability function, if you take the standard part of it, so that means if you have, so it will assign to an event A, say something like a real number R plus some epsilon thing, something of a really small, of infinitesimal probability. Forget about this. Just look at the real part. That's the standard part. So the probability of A, something like that, will be a non-standard number, but it will have a real part. Throw away the non-real part. Well, then of course you can write probability of A given B. That's defined in the usual way in an framework. This will also be a non-standard number. Throw away the real part, it will give you a real number. So you can have the standard part called A. Look at that. This will always be a Popper function. And this is kind of easy to see. You just go through all these non-intuitive axioms, there are not so many of them, routine. But then there's the other direction, which is different. Given a non-Archimedean probability function, is there a conditional probability function that's infinitely close to it, point-wise? Yes. So that means that this non-Archimedean probability stuff relates to things that people are actually interested in. Okay, that's one thing. Secondly, lexicographical probability functions. This is another way in which people are trying to generalize probability functions. What they say, these lexicographical probability people, say the probability of A is an omega sequence of real numbers between 0 and 1, let's say. And okay, when you work with these things, they will be finitely additive and they will be related to conditional probability in a certain way. So there is a community that works with this lexicographical. How do they relate to the NAP function? What one well, it's known that there are lexicographical probability functions of this kind. So this is an omega sequence that cannot be represented as non-Archimedean probability functions. And people have wondered, well, is there a way of generalizing this lexicographical probability function stuff so that it can be done? And I think, well, I'm not going to go into details about this here either, but what's wrong in here is the well-foundedness of this, right? So what you should roughly see this as follows. This is R0, a real number, to epsilon to the 0, plus R1, 2 times epsilon to the first, plus Rn times epsilon to the n, and so forth. Where these are degrees of infinitesimality. That's how you should see it. And for finitely generated languages, this is how you can see it. This is a theorem by making it. But it's a theorem. But the reason why this won't be enough is that the structure of degrees of infinitesimality that we're dealing with is non-well-founded. It has to be the non-standard thing. This is the non-standard. The whole thing is the non-standard reals and values. So that means that if you look at the structure of degrees of infinitesimality, you can define it in this framework, but it will be a non-well-founded structure. So what you can try to do, and I think it can be done, is to say, well, then represent one of these non-standard probability functions in a kind of a normal form like this, except that this will be a non-well-founded series. Okay, so this is just a big claim, no proofs. And then, yeah, you can also try to relate it to Banach limits, which have a shift property. So you can ask yourself, for instance, can I define my probability functions in such a way that the standard part of it will be a finitely additive probability function, which has the shift property? In other words, is a Banach limit. You can ask yourself questions like that. So, last slide. You can also say, well, can I extend this to mathematical universes? So can I ask myself the following? What does it mean for a property of sets to have a probability of being true of a set? And of course, this would mean if you go about trying to do this, then you're talking about ultra-focus over the universe. I don't have any problems with it, but you know, it's these the reasonable models of the universe are the accessible cardinals. So you can try to identify properties with their extensions, so they can be proper in proper classes, and develop a theory of the probability of events of the form A of y, where A is a class, the variable proper the variable y is a random variable ranging over all set. Then you can ask yourself questions like, given that there is a measurable cardinal, what's the probability that a set is a number? Should be 0.